All right, so welcome back. We are still in section 1.4. And the new equation that we are going to be tackling is a multiplied by x. Let's make sure we understand. So the a, in this case, represents some m by n matrix. Right? So the a represents some m by n matrix. So it could be a 3 by 4. It could be a 3 by 3. But it represents some m by n matrix. Now, the x in this little equation represents a vector, okay? And the vector must be in, so you got to think about, you could have vectors in 2 dimensions or 3 dimensions, right? That would be R2 or R3. But this vector must be in the dimension Rn. Now, let me see if I can, first let's just draw attention to the n here and the n here must match. Okay, so kind of looking through the definition, this kind of hinted at what's happening. So again, A is some m by n matrix with with columns a sub 1, a sub 2, a sub 3, all the way to a sub n. Now that I'm going to erase this, but that should make sense. So matrix A is some m by n, and the columns, so we can think about a sub 1 is the first column, a sub 2 is the second column, etc. Now, so given that, and x is some vector in the space Rn, and here it is, then the product of a and x, meaning a multiplied by x, the product of this of a m by n matrix and a vector in Rn, the product is the linear combination of all the columns of A using the corresponding entries in X as the weights. So what you're seeing here, this is your matrix A. This is your vector X. And listen, don't let this language confuse you. All we're saying is if you want to multiply these two, right, then the outcome is as follows. And what they're saying is, notice that the x sub 1, the x sub 2 are the weights, the scalars attached to your columns of matrix A. All right, I understand that can be somewhat confusing. So let's jump right in to example 1. And now you're going to see how do we multiply matrices, right? So in this case, we have, this is matrix A, and it is a vector. It can be viewed as a column vector, but it's written in this matrix form. And what I want to do is I want to go ahead and so this first one has 2 rows, and it has 1, 2, 3 columns. Now let's go to this vector. This vector has 3 rows. And of course, since it's a vector, it only has 1 column. Structurally, this is very important. Structurally, these two must equal each other in order to multiply. I'll say that one more time. Just like if you want to add 2 matrices, you can only add a 2 by 2 matrix to another 2 by 2 matrix, right? Structurally, it only makes sense this way. Likewise, if you want to multiply matrices, you can only, and I mean only, multiply matrices if the number of columns in the first matrix is equal to the number of rows in the second matrix. If that doesn't equal, right, if this were a 1 by 3, then you would get an error if you tried to multiply them. But given that they are the same, how do we proceed? Well, if you've had any exposure to matrices, when you multiply matrices, we multiply rows by columns. So let me see if I can guide you here. So we're going to be multiplying this row by this column. Look at my highlights. Row multiplied by column. Then it's going to be row multiplied by column. And then finally it's going to be row multiplied by column. So let's do it. So rows multiplied by column. So this is going to be 4 multiplied by 1, 0 plus 3 multiplied by 2, negative 5 plus 7 multiplied by negative 1, 3. Again, row times column, row times column. Now, so let's go ahead and finish this up. For part B, I'm going to just give you the answer, and then you should take your time and see if you can and work it out the way that we've worked it out here. But let's go ahead and finish this up. So we're going to do right now is just go ahead and distribute that 4, that 3, and that 7. Before I do, remember the language that I was using up here that probably was confusing, where we said X, the entries in X as weights. Well, X was the vector, right? Do you see how the entries in the vector become the weights or scalars of the columns? So hopefully now that makes sense. But let's go ahead and multiply this out. So we got 4 times 1, 4 times 0. And then we have 3 times 2, 3 times negative 5. And then finally we have 7 times negative 1 and 7 times 3. So negative 7 and 21. So finally, at this stage, we can add. So this is structurally, right? This is a 2 by 1, and this is a 2 by 1, and this is a 2 by 1. So you definitely can add them. Now I'll show you one more thing that's pretty. Structurally it would have to be, but it can be a good trick, and it's also quite interesting. But nevertheless, so when we finally finish adding, it's just going to be 4 plus 6 minus 7. That's going to be the first entry. All right, so we're adding corresponding entries. And let's see here. So that should give us, 4, 6, 10 minus 3, so that's 3. All right, and the next entry is going to be 0 minus 15 plus 21. So minus 15 plus 21, so that's 6. All right. So the product of A times X is what you're staring at right here, 3, 6. That's the result. Now, I am going to give you the answer to B, but listen, let me show you something that's really neat. So do you remember back here I wrote the dimensions of the matrix and, of course, the dimensions of that vector X. And you can recall I mentioned that these have to match in order to do the multiplication. If these don't match, then you just can't multiply them. Now, notice that what's left over, this 2 and 1, 2 by 1. And notice the result was a 2 by 1 matrix. So these two here must match in order to even multiply, and these two on the outside is actually the form of your answer. Quite interesting. So let me go ahead and, so for part B, the answer that you should get is negative 13, 32, negative 6. You should either pause the video or sometime on your own time make sure that you can produce that from that multiplication. All right. So let's see if we can shift through example 2 and figure out what it is that they're asking. So it says, example 2, so for v sub 1, v sub 2, and v sub 3, in some space Rm, right? So what I mean is we could be, like these vectors here could be in 2 dimensions. It would be R2. Those 3 vectors could be in 3 dimensions. That would be R3. We don't know what M is, but whatever M is what dimension that we're in. Okay, so for the following v sub 1, v sub 2, v sub 3 in dimension Rm, we would like to write the linear combination as a matrix times a vector. Okay. This question is asking you if you go the opposite direction from example 1. In example 1, you had a matrix times a vector, and then you were able to get to here, a linear combination. Imagine if you started here with the linear combination and you wanted to get back to a matrix times a vector. That's what this question is asking. So we're working our way backwards. So what we want is AX. So we need to figure out what A is. We need to figure out what X is in order to place this in AX form. Well, all right, so here it is. So this is the linear combination. This is the equivalent of our step right here. And now we're going to try to work backwards. So if we were working this problem backwards, the weights, the scalars, the 4, the 3, the 7, those are all entries in our vector, whereas these little vectors here form the columns of matrix A. So if that's the case, then I think it should make sense that looking at our linear combination, let's start with the weights. So we got a weight of 3, a weight of -5, and a weight of 7. Just like here, we had a 4, a 3, and a 7. So those should serve as entries in vector X. So 3, -5, 7. Okay. Now, matrix A is going to be built, the columns of matrix A is built from V1, V2, V3. We don't know what V1, V2, V3 are, right? Here we did. If you were here, we know V1, V2, V3, so we could actually get to this 2x3 matrix. But if they don't tell us what V1, V2, V3 are, we don't even know the dimension that these vectors are in. But that doesn't matter. What does matter is that whatever these are, V1, V2, V3, they're going to serve as the columns of matrix A. So now, what is the form AX? It's just, so A is going to be V1, V2, V3. And X is going to be 3, -5, 7. That is how you would write That is how you go from a linear combination back to a matrix times a vector. Okay, so this part's the A, this part's the X. I hope that makes sense. So the next theorem, theorem 3, it's going to reaffirm the things that I've already told you. But let me read it. So it says, so here's the if statement. So if A is some m by n matrix with columns a sub 1 through a sub n, and if B, we'll say, is some vector in the dimension Rm. So with that information, there are 3 different ways. Listen, this equation 4, the equation 5, equation 6 are 3 different ways of writing this information. So this first one is the matrix equation. Let's go ahead and write that. Let's write the name beside them. So this is the matrix equation. This is the vector equation. And this is the augmented matrix, or the system. Of linear equations. 3 different ways of expressing that information. 3 different ways of solving that information. Now, the next portion that we want to take a look at is back to existence, right? Existence of solutions. So I mentioned that two of our primary questions in linear algebra is A, is the system consistent? Right? A consistency would mean that you have at least one solution. Could be more, but at least one. So first question you want to ask is, hey, is there even a solution to the problem that you're trying to solve? That's the first question. Is it consistent? Now, if the answer to that question is yes, there's at least one solution, then the next question we like to ask is, well, is that solution unique? Right? In other words, is that solution the one and only one solution, or is it just one of an infinite amount of solutions? All right, well, with that in mind, let's kind of read through this little definition. So, existence of solutions. So the definition of AX, now remember, AX, we've already kind of discussed that, leads directly to the following useful fact. And here it is. The equation AX equals B has a solution if and only if B is a linear combination of the columns of A. Well, again, this can be just something you gloss over, but what that's trying to say is, look, if you'll lend me your ear for just a little bit longer, AX equals B has a solution if and only if, here it is, look at this vector equation, if and only if B is a linear combination of the columns of A. Right? So hopefully with me, using my stylus and pointing to the important parts of that definition, that hopefully that helps. Hopefully that helps elaborate. Now, the next question is a good one, but it is slightly involving. So it's involving only in the not in the theory part. There's no new theory for example 3, but it is involving in just the tedious nature of these row operations. So what I've done, I'm going to read the problem, but I'm on the next page, I've already worked out the little tedious row operations, and you can, when I flip to the next page, you can pause the video and you can write those notes. Again, nothing that you haven't seen before, but I've already wrote them out to save us a little bit of time. Let me now read the question. It says, so let A be the following matrix, and let's let B be the following vector. Okay. The question is the equation AX equals B, there it is, consistent for all possible B? All right, so let's see if we can make sense of this. So first off, matrix A, well, we can all see that's a 3 by 3 matrix. So let me go ahead and write that. 1, 4, -3, 3, 2, -2, 4, -6, -7. So, all right, so we have a 3 by 3 matrix. That would mean that there's 3 equations and there's 3 variables. Or well, I misspoke. It could be 3 equations and 2 variables, right? This would be the solution region if it's an augmented matrix. Okay, so now we have vector B. So you can imagine that vector B is a point in 3-dimensional space. The way I would view this is, let's think about length with height. So if I have length B sub 1, width B sub 2, height B sub 3. So if I move over B sub 1 and then up B, and then again move to B sub 2, and then I move up height-wise to B sub 3, I would reach a single point in 3-dimensional space. Now, clearly there is an infinite amount of points in 3-dimensional space. The question you are trying to figure out is, hey, is it possible with matrix A, is it possible to reach any point in 3-dimensional space? Or are we limited? So to do this, we need to start with matrix A, and we need to start with some row operations, right? So the first thing the way you want to think about it is, we're going to build a matrix. Oh, I was correct when I said that this is a 3 by 3 matrix. This is a coefficient matrix, so there are 3 variables. This is going to be our solution region. So let me go ahead and show you where we're going to go from here. So typically what you would want to do is you would want to RREF a matrix, right? But you need to have a matrix to row reduce. So the question becomes, how do you build a matrix so that you can row reduce? Well, the matrix is built from this information here given. Let me go ahead and write it. So we already know column 1. We already know column 2. So 3, 2, -2. And we already know column 3, 4, -6, -7. The thing that we don't know is that last column, right? Which we are using B sub 1, B sub 2, B sub 3 as placeholders. So now you can see that, quite unfortunately, since we're using variables here, this is not something we can outsource to technology. So we would have to use row operations by hand. I'm now going to move to the next page. Just remember, when you're trying to run that row reduction algorithm, if you're going to try to run the algorithm, remember, think about the goals. You want zeros here. You want ones along that diagonal. So triangular form, ones along the main diagonal. This would be the row operations to get you there. Again, you can pause the video and look through this little bit of row reduction. But I'm going to more or less draw attention to the results. So notice, see how I'm in triangular form? And I actually have enough information right here to be able to answer this question. So I'm going to scroll back. If you need to pause the video, feel free to, but I'm going to scroll back. And let's go ahead and let me give myself a little bit of space. And this was the result of that previous page. All right. So what I'm going to do right now is I want to draw attention to that third row. Well, so that third row, if I were to write that third row as an equation, it would be 0 is equal to b sub 3 plus 3b sub 1 minus half of b sub 2 plus 4b sub 1. And now, what I'm going to do is I'm going to distribute, and then I'm going to combine like terms. Okay? So if I were to distribute and then combine, here is what I would be left with. Okay. Now, let's get back to the question. So what even was the question? So the question was, is this equation consistent for all choices, all possible b sub 1, b sub 2, b sub 3? Well, where we finished off, we can view this as, I think you and I would agree, there are some numbers out there. So there are some b sub 1, b sub 2, b sub 3 out there that if you plug those in, you can arrive at 0. Right? So, I mean, let me see if I can make up one. This might be an utter failure. B sub 1, B sub 2, B sub 3. But let's see if I can make up one. So, well, that's the easy one. 0, 0, 0. So clearly, if b sub 1, b sub 2, b sub 3 are all 0, then that equation holds true. And if I sat here, I could probably think of some more. But the real question, and the question to you is, can you think of some values that would not work? Well, that is pretty quick. If you were to pick, for example, 1, 1, 1, this would be 1 minus a half plus 1. That does not equal 0. So that would mean you cannot reach the point in space 1, 1, 1. You cannot choose 1, 1, 1 for your values in that vector. So the question is it consistent? Well, to the question of is it consistent, the answer is yes. But the real question was, is it consistent for all possible b sub 1? And the answer is no. Although there's some of the values work, it is not consistent for all the b values. like we just showed. 1, 1, 1 does not work. So in terms of your geometry, again, you can, well, actually, I'll tell you what, I'll hold off on the geometry part for the next video. But hopefully this is starting to click. Hopefully it's starting to make sense. And I will see you in the next video.